Hello my viewers, in this video lecture we are going to cover the second part of the design example of T-beam girder bridge. Already in the last video I have covered the first part of this design example. So the last video I shall provide in the description box. So this is the design problem. So in that design problem, in this video lecture, we are going to start from the design of longitudinal girder. Already in the last video, we have covered up to the design of slab panel. So for the design of longitudinal girder, first of all, I have to calculate the reaction factors for the longitudinal girders. Using Kurban's method, IRC class A wheel loads are arranged for maximum eccentricity as shown in figure 4. So this is the arrangement of the wheel loads on the girder. These are the wheel loads. So first of all, we have to understand these dimensions. You see, for this IRC class A loading, from the edge of the pavement or the bridge to the face of the wheel or track, the distance is 1200 mm. So from the edge of the bridge to the center line of the wheel, it will be 1200 plus 850 by 2. So it will be 1625 mm. So in this figure, this distance is 1.625, and the center to center distance between the longitudinal girders are 2.5 meter each. So by understanding this dimension, we can easily calculate the other distances or the dimensions we have used in this figure. Another important dimension you have to understand, that is the center to center distance between the 2-point load. See here, the inner face to face distance between the two wheels is given which is 1200. Okay, so the center to center distance between the two wheel load will be 850 by 2 each on the each side. So this will be plus 850. So it will be finally 2050 mm, which is the center to center distance between the two wheel loads. So that's why it is given as 2.05 meter. The rest of the values we can easily calculate. Here another dimension you have to understand, that is the eccentricity, E. So what is E? It is the distance between the central axis of the bridge and the CG line of the load system. The CG line of the load system, W1 to W1 will be at the midpoint of this load system, and distance between this will be E, which is called eccentricity. So following the other dimensions, we can easily calculate E equal to 1.1 meter. So let's use the Kurban's method. So first of all, I will calculate the reaction factor for the girder A, that is the RA, and this is the formula. We have two wheels each having load intensity W1. So summation of W will be W1 plus W1. N is the number of girders, which is equal to 3. Then summation of I equal to moment of inertia for each girder. So for each girder, moment of inertia is I. So finally it will become thrice I. Again, what is dx square into I? See, dx is the distance of one girder from the axis of the bridge. So for the girder A, the dx is 2.5. dx square into I means 2.5 square into moment of inertia of the girder A, which will be I. Again, for the girder B, the dx will be 0, as already the girder B is placed on the axis of the bridge. Next, for the girder C, the dx will be 2.5. So dx square will be 2.5 square for the girder C. So dx square into I equal 2.5 square into I for the girder C. So in the equation, this is for A and this is for the girder C, and for the girder B, dx will be 0. Now this dx is for the girder A, as we are calculating the reaction factor for A, and this is the eccentricity. Already we have discussed what is the eccentricity. So after the calculation we will get RA equal to 1.107 W1. Similarly, we have to calculate the reaction factor for the girder B. Here the difference is this term will be 0 because the girder B is located over the axis of the bridge. So for the girder B, dx is 0. So these terms will be comes out as 0. And after the simplification, RB equal to 0.667 W1. Here two wheels are acting on the girder. And for IRC class AA track vehicle, the total load W is 700 kilonewton. So for each wheel, it will be half of W. That is, for each wheel it will be 350 kilonewton. So W1 equal 0.5 W. So RA becomes 0.5535 W. Similarly, the RB becomes 0.3335 W. Now we have to calculate dead load bending moment and shear forces in main girder. In the figure, the overhang portion of the bridge is shown. So dead load we will calculate in per meter width. Now self-weight of the parapet railing. So this is the parapet railing. This portion is the parapet railing of the bridge. So which is 0.7 kilonewton. Then self-weight of wearing coat. So remember, in this calculation, all the calculations will be done from the face of the outermost longitudinal girder. So for wearing coat, 80 mm is the thickness, which is 0.08 meter, which will be multiplied by the distance 1100 mm or 1.1 meter. Again it will be multiplied by the self weight, which is 22. So it will comes out as 1.936. Similarly, the self weight of the deck slab. So for the deck slab, the thickness is 200 mm. Then its length is 1.1 meter, and the self weight of the deck is 25. So finally we will get 5.5 kilonewton. Then self weight of curve. So this is the portion of the curve. So it is 500, total 500 mm. So the area is 0.5 into 0.6, which will be multiplied by the unit weight, which is 25. So finally 7.5 kilonewton. So if I sum up all this load, so I will get 15.636 kilonewton. See, this load is, or this weight, this self weight is only for the overhang portion of the bridge. If you see along the cross section of the bridge, it will have two overhang portion in the both side. So if I calculate the total dead load of the deck slab per meter width, so it will be multiplied with 2 into 15.636. Then this is the self weight of the slab panel, which is already we calculated in the part 1 of the video. Means we have discussed in the last video where we designed the slab panel. Now what is the 5.3? See, here all the distances we calculated from the face of the outermost girder. Okay, now see, the center to center distance between the two outermost girder is 5 meter, 2.5 and 2.5, total 5 meter. So if we include, this is the girder, these small distances in both sides, so this distance will be 5.3. Means we have to add the half of the girder width in the both side. So finally it will be 5.3. So this is the self weight of the slab panel and this is the length. So finally we will get the total dead load as 67.1 kilonewton. So if you assume the dead load is equally shared by all the girders, so the dead load for each girder will be 22.37 kilonewton per meter width. So already we have assumed the length is 1600 mm, the width is 300 mm for the longitudinal girder. So now the depth of the rib. See, if it is the main girder, this portion is called rib below the slab. Means if the total depth is 1600, so if you subtract the depth of the deck slab, we will get the depth of the rib. So it is the depth of the rib. So therefore the self weight of the rib, it is the width of the girder, that is the depth, and this is the self weight or unit weight of the concrete. So it will comes out as 10.5 kilonewton. Also we have assumed the longitudinal girder and cross girder has the same cross sectional dimension. Therefore the self weight of the rib of cross girder also will be 10.5. Next one important thing we have to understand is we have 3 main girders. Okay, and these are connected by 5 cross girders. So at every joint, the load of the cross girder will act as a point load on the main girder. So At this joint, the half of the cross girder in one side and half from the other side will act as a point load. So for each cross girder, the length is 2.5 meter. So this will be half of 2.5 and this will be half of 2.5. So that means total 2.5 length of cross girder self weight is acting as a point load on every joint. So that's why the reaction from the cross girder on the main girder will be 10.5 into 2.5, which is 26.25 kilonewton, which is acting in this way. Okay. Now the reaction from the deck slab on each main girder is 22.37 kilonewton per meter, which is already calculated. Now the total load on the main girder is 22.37 plus 10.5. See, 22.37 is the self weight of the deck slab and 10.5 is the self weight of the girder itself. So 32.87 kilonewton per meter is the ideal acting on the main girder. This is 32.87, and the weight of the cross girder will act as the point load at every joint of the main girder. So this is the dead load on the main girder. So based on this, we have to calculate the maximum bending moment and shear forces. See, referring to the figure 6, the maximum bending moment is to be computed. Okay, so for this system, so first of all I will calculate the support reactions. These are two support. So if you observe very carefully, the load system on this girder is symmetrically placed, means the girder is symmetrically loaded. So both the girder will carry the half of the load acting on the girder, means both of the support will have the same reactions and it will be the half of the load acting on the main girder. So this is the support reaction we have calculated. This is the ideal into the total length, and this is the point load, and we have three numbers of point load. So total load divided by 2 will give us the support reactions at the each support. So then we have calculated the maximum moment, and it has comes out as 1261.88 kilonewton meter. So next is the maximum shear force at the support is computed as, see, all of us know that the support reactions in maximum cases, the support reactions give the maximum shear force. So the Vmax is equal to the support reaction. So it will be 302.34 kilonewton. Next we have to go for live load bending moments and shear forces in main girders. So first of all we will calculate live load bending moment. For IRC class AA tracked vehicle, total weight of 700 kilonewton is acting through a span of 3.6 meter. So if I convert this load into UDL, it will become 700 divided by 3.6 kilonewton per meter. Now, so I have written UDL in the form of will be 700 divided by 3.6 kilonewton per meter. For the maximum bending moment of live load, the load is placed centrally on the span as shown in figure 7. So it is the longitudinal girder. The load of class A track vehicle is placed at the central position of the main girder or longitudinal girder, and UDL is 700 divided by 3.6. So then I will draw the influence line diagram which will give us the maximum bending moment. So if I calculate the maximum bending moment, so it will be the total area will be multiplied by the UDL. So this is the area under the influence line diagram for this small portion, and then it is multiplied by the UDL, and it will give us the maximum bending moment. Then impact factor for IRC class A track vehicle for span of 16 meter is 10%. Now again, if we apply the impact factors as well as the reaction factor which is already calculated, so the bending moments for outer girder will be comes out as 1513 kilonewton meter, where the maximum bending moment will be multiplied by the impact factor as well as with the reaction factors. Then for the inner girder, it will be comes out as 911.62 kilonewton meter. So these are the bending moments for outer girder as well as the inner girder. Now we have to calculate the shear force for the live load. To calculate the shear force for the live load, so you have to place the class AA loading as shown in the figure 8. As all of us know that the shear force becomes maximum when the load is nearer to the support. So these three are the longitudinal girders. So the load is placed in such a way that it is nearer to the support. That's why it is placed over the girder B, and with reference to that wheel or track, the other wheel is also placed at a distance 2.05 meter. Now reaction of W2 on the girder B. See, for the W1 which is directly placed on the girder B, the load of the W1 will be directly taken by only the girder B because it is placed over the girder, directly over the girder. But for the load W2, it is placed over the panel. So the load W2 will be partially shared by the girder B, as well as some part of the load W2 will be taken by the girder A also. So reaction of W2 on the girder B, so it will be 350 divided into 0.45 by 2.5, means 63 kilonewton of W2 will be taken by the girder B as it is away from the girder B. At the same time, when I calculate the reaction of W2 on the girder A, it will be 350 into 2.05 divided by 2.5. Then 287 kilonewton of the load W2 will be taken by the girder A. So these expressions are similar to the calculation of support reactions. So we have some formulas to calculate the support reaction, W into B by L. So it is like that. W is the load, B is the distance of the load from the other support, not from that support where I am calculating the reaction. It is from the distance of the other support to the load. So as I am calculating the reaction for girder A, I am taking the distance from the girder B. Okay, so one will be 67, the other will be 287. Next, the total load on the girder B. As I already told, the W1 load will be directly taken by the girder as it is placed on the girder. So it will be total 413 kilonewton. Now the maximum reaction of in girder B. See, the girder B will take at this position, the girder B will take total amount of 413 kilonewton of load. Now if you see in this direction, this is a longitudinal girder, what will be the support reaction here and here, and the point of application of load is here. So it will be W into B by L. So here W will be 413, B is, if I calculate the reaction at this point, so B will be 14.2, L is the total length 16, so it will be comes out as 366.54 kilonewton. Similarly, for the girder A, it will be comes out as 254.71 kilonewton. So if I apply the impact factors, finally for the outer girder it will comes out as 280, for the inner girder it will comes out as 403.19 kilonewton. Some may ask that why I have, if for this longitudinal girder, why I have taken this reaction, this support reaction, not this one. Because as the load is acting near the support, so here the reaction will be maximum and that will be the maximum shear force. Is it clear? So that's why I have calculated the support reaction at that support which is closer to the load. That's why this support reaction I have calculated. So this is the design bending moments and shear force. So I have shown all the bending moments and the shear forces for dead load as well as the live load in the form of one table, and then I have calculated the total bending moment as well as the total shear forces. So all the values I have gathered and formed one table which will help in our next design part of the girder. See, we have started the design of the section of the longitudinal girder. So this is the maximum bending moment and this is the maximum shear force. So the longitudinal girder will be designed as a T section, assuming effective depth as 1450 mm. So the total depth we have 1600 mm. So we have assumed the effective depth as a 1450 mm. Then if I calculate the area of reinforcement, this is the formula for AST for the working stress method. So I shall put the values of sigma ST. Already I have shown how to take the values from the IRC code in the last video. Then J is already calculated 0.902. 1450 is the effective depth and here is the maximum bending moment. So it only comes out as 10,608.15 mm square. So this is the required area of reinforcement for the maximum bending moment. So if I provide the 32 mm 32 torr bars, then the required, sorry, it will be, oh sorry, the bars required for the section will be comes out as 14. So we'll provide the 16 numbers of 32 bars in 4 rows. So you may ask that though 14 numbers reinforcements are enough, why we are providing 2 more reinforcement? Because to have the enough space in between the reinforcement, we will provide the reinforcement in 4 layers. Okay, and when I provide the reinforcement in 4 layers, all the layers should have the same number of reinforcements. So I shall provide the reinforcement for each layer have 4 numbers of reinforcement, and it will be finally 4 into 4 layers, it will be 16. Okay, and we will provide the area of steel 12,867.96 square. This much will be the area of reinforcement I have provided. Next I will calculate the nominal shear, which will V divided by BD. So maximum shear force divided by the cross sectional area, it will comes out as 1.622 Newton per square. Then if you see the table 12A of IRC 21 for M25 grade of concrete, tau max is 1.9 Newton per square. So as per clause 304.7.1.2 of IRC 21/2000, tau is less than tau max, hence safe. So always the tau should be less than tau max. Among the 16 numbers of 32 bars, if we provide 2 numbers of 32 bars as a bent up bars near the support on each side, then the shear force resisted by the bent up bars is given by this formula. So in this formula, sigma SB is the permissible shear stress of steel, which is 200, and this is the area of reinforcement which will act to resist the shear force, and 45 degree is the angle of the bent up bars, which is provided at 45 degree angle. So the force, the shear force resisted by the bent up bars will be comes out as 227.48 kilonewton. So therefore the balance shear force after partially resisted by the bent up bars will be total shear force, which is V maximum minus V S dash, which will be comes out as 478.05 kilonewton. Now the percentage of tensile reinforcement corresponding to the maximum tensile reinforcement provided will be comes out as 2.96. Now from the table 12B of IRC 21, see this is the table 12B of IRC 21 for 2.96, which is approximately 3.00. For M25 grade of concrete, the sigma, the tau C value is 0.57. So that's why I have written it is 0.57. So as per clause 304.7.1.4 of IRC 21/2000, the shear reinforcement shall be provided to carry the shear force of the following. So Vs equal to V minus tau C BD. So 478 minus 0.57 into 300, which is B, and 1450 is the effective depth, into 10 to the minus 3 to make it in kilonewton. So finally comes out as 230.10 kilonewton. So for this much of shear force, we have to design shear reinforcement. Using 4-legged 10th bars as vertical stirrup, the required spacing is calculated as follows. So this is the formula which is given in the IRC code. So spacing will be equal to this. So where ASW is the area of shear reinforcement, which is this one, then sigma S is the permissible stress of steel, which is 200. Then D is the effective depth, and as I am going to provide the vertical stirrup, so angle will be 0 degree. So sin 0 plus cos 0, and Vs is the shear force for which I am going to design the stirrup, which is 230.10 into 10 cube. So the spacing will comes out as 395. This is the required amount of spacing, or the spacing required. Now, as per clause 304.7.1.6 of IRC 21/2000, the maximum spacing can be provided as 300 mm. So we can provide the spacing up to 300 mm. Therefore, I shall provide 4-legged 10-third bars as at the rate of 300 mm center to center as the vertical stirrup. All about the design of the longitudinal girder for bending moment as well as for the shear force. In the next part, we shall design the cross girder for this T-beam deck slab type of bridge. So if you like the video, please share and subscribe. Thank you for watching.